Intermolecular forces. The forces that act between molecules. Okay. How big is a molecule? Jasmine, how big is a molecule? In comparison to the width of a hair. So pluck out one of your hairs. Look how wide it is. Smaller, yeah. But what fraction of the width of a hair would you guess a molecule is? Millionth is, no. Then you're getting below the size of an atom. Because a hair is already 10 to the negative 6 meters. It's about a micron. I'm talking about one single hair. One single hair strand, right? And that's about, so it's about 1,000 to 10,000, 1,000 to 10,000 times, right, more thin than a hair. So we're not even talking about the forces that act within that extremely small molecule. We're talking about the forces that act between them, which sometimes is more important for real life because it's much more applicable, okay? And we see it all the time. It has cause and effect with what we're doing. If we, well, let's try to get some misconceptions, or maybe it's not a misconception. Okay, surface tension. Made a little boat. Good deal. Crystal Munoz, why is that boat floating? Is it because of surface tension? She says buoyancy. Is it because of surface tension? Don't they work together? Does surface tension help buoyancy, is that what she's saying? Why do boats float? Anybody? Boats are heavier than water. They should be sinking. Like, see in the bottom? I took the same ball of clay and I just rolled it up in a ball and dropped it in there. I don't want to dig it out, but you have to trust that it would sink, right? It's the same clay. It's the same stuff. One sinks. Why? The D word, not damn it. Density. Density. This is a really neat thing to play around with your board this weekend, right? You get some clay, and it's made in the shape of a box because then I can. That's my little dude, right? It's made in the shape of a box, so you can measure length times width times height, so you can actually measure the volume. And then you're gonna have to mass it somehow, though.
You made the density?
Yes, this is like 50 grams. So divide the mass by the volume, you get the density. It doesn't matter. This always works. If this density that you calculate for this boat is less than what grams per mil, it's going to sink in this water. What's the density of water? 1 gram per mil. If this density is, sorry, not less than, bigger than 1 gram per mil, right, it's going to sink like a rock. If it's less than 1 gram per mil, no, it'll float. So density is mass over volume. So if I can make the same hunk of clay bigger, it'll be less dense. How do I make it bigger? Well, look at all the empty space in there, right? That's the whole idea of a boat, just to have a whole lot of empty space. So then the density drops like a rock. The density decreases. So instead of your boat dropping like a rock in the lake. So it's not because of surface tension. You can actually kind of tell it's not because of surface tension because the surface is broken. Right? The boat's below the surface level, so it's definitely not surface tension. Okay. So what is surface tension then? This is kind of a nice picture of surface tension. The dot is supposed to be the molecule, and the arrows are just the interactions with all the other molecules, the intermolecular forces. And if you're in the bulk, they're in all directions. If you're on the surface, they're not. They're not in all directions. The surface is actually has very different properties than the bulk. We did a research experiment where we were trying to figure out, find ibuprofen. What's ibuprofen? Yeah, you know, you have a headache, you pop some ibuprofen, right? Or pretty much any medication you take, how much does your body chew up and metabolize? It's a lot smaller. Only like 1 or 2%. So everything else you just whiz out. Where does it go? The streams, the lakes, everywhere else. This stuff is building up in the environment. So that was our research project. Can we detect ibuprofen in this river or this lake over here? So, but it's really dilute. So what we did is we didn't just take a cup and just sample the water. No, we skimmed along the surface because the surface has a different property and it concentrates a lot of the bad stuff, a lot of the contaminants. Okay. So the surface tension does have different properties than the bulk.
What did y'all find? Y'all found it?
Yeah, but it's so trace, it's really hard to. The instruments, our technology aren't quite good enough. However, what we did find with a different project, same idea, but let's analyze the water going into your sewage treatment plant and the water going out of the sewage treatment plant, because everything's much more concentrated. So, and we were looking for, again, any drug we can find, and we found Tylenol, and we found naproxen of all things. What's naproxen? Anybody know? If you have high blood pressure. So it's a very common high blood pressure medication. So we found those two. Both going into the sewage treatment plant and going out. So that, yeah, sewage treatment plants are not built to do that. They're not built to get organics out of the water. Okay, so surface tension. Here's some different liquids, and they all have different surface tensions, some bigger than others. So if you notice the units of surface tension, joules per square meter, what's a joule again? That's the unit of what? Heat, or in general, energy. How about meters squared? Area. Good. So what surface tension is just it takes energy to stretch a liquid, the surface of a liquid. It takes energy to stretch it. And some solvents, some liquids are easier to stretch than others. So it's just like a spring. It's stretching. So the spring is, and you can have stiff springs, you can have springs that are easy to stretch. So surface tension is just like that. Some liquids, man, it's so hard to stretch them. This spring is extremely hard, it's extremely stiff. But others, yeah, it's really easy. So there's something going on here between these molecules, these intermolecular forces. They're different compounds and they have different intermolecular forces, some stronger, others not. And we'll get into identifying them in a little bit.
Isn't the non-Newtonian fluid the kind of thing, they have videos on the internet about people kind of running and dancing on?
Ooh, that's exactly, you know what Crystal's talking about? Man, I couldn't ask for a better lead-in. Say it louder.
People can actually dance and walk all over this type of fluid, and you find really interesting videos online about it.
Wow, what a good idea. Let's do that. A pool filled with a non-Newtonian fluid. Now, only if you're Spanish speaking, you're going to understand what they're saying. But it's still fun to watch. If it works. Oh no. Just what? Where's the refresh? Oh, this guy. Yeah, then I'm going to do the stupid commercial again. Ah. All right, we don't have sound. Well, what did he say? Oh. Yeah, he's floating in it. Okay. So that
That's so
non-Newtonian, it's really easy to make. What they did is they took cornstarch and they just added some water. But you got to add the water slowly, and then until you get what you want. And it's just very strange because you're going to take this and you're going to want to. It just responds the opposite way a regular liquid would. If you stir water. Does water get easier to stir or harder the harder you push? Easier, right? I mean, that's just nature. You're used to that all the time. The harder you push, you expect your spoon to move faster, right? That's just how things work. That's Newtonian. Non-Newtonian, it's the exact opposite. The harder you push, it locks up. You have to push really easy, and then it's as slick as snot. Just whew, if you don't push very hard at all. So what they believe, how they believe this works, is cornstarch is made up of these starch molecules which are extremely, extremely large and bulky. So the only way you can get them to move out of the way, right? Because if you're going to stir, they have to move out of the way and move around, is if you don't push really hard on it. Because the only way they can move around each other is if there's a very thin layer of water between them. And if you push hard, the water gets pushed out of that interstitial spacing and they just lock up. So when you try this, I made this from the last class period. I mean, I can't, to this day, I can't. I've been playing with this a lot, and I keep pushing harder, but it doesn't move. You got to just barely push on it, and you can go across. Okay, just barely push on it, and it moves. But you push hard, it just locks up. It locks up even harder. All right, I'm trying to get this stirred up better before I hand it to you. See if I can get it a little bit better stirred up. Then it'll respond better. It's so hard to stir, though. Gotta go slow, and then it'll stir. But play around with it. You'll see. After you play around with it a little bit, it makes me feel like that guy who was in that pool, if he did go under, and if he did get it in his mouth, and if he swallowed it, his esophagus is trying to push this stuff out. And the harder it pushes, the more it locks up, right? That would have been horrible, right? He has to totally relax and just, I don't know, just somehow swallow it, but in a very relaxed way. But that's not natural. You're going to want to go, ugh! Give me the Heimlich, give me the Heimlich. Oh, that's just the opposite. It is not going to work. Okay, so these intermolecular forces, there's 3 of them. We're going to watch an animation of each, and then we'll make some general ideas from them, like what's the strongest and how can we increase the strength of each intermolecular force. Okay, the first one is London dispersion animation.
In solid carbon dioxide, dry ice, nonpolar molecules are arranged close to one another in a regular array where they move slightly around an average position. The distribution of electrons in a molecule can occasionally become asymmetrical, leading to the...
Okay, now this is going to get really ugly soon, but because they use a lot of heavy language in here. But from the very beginning, they said this was what ice? Dry ice. And that compound is what? Carbon dioxide. Is it a... we lost it. Is it a linear molecule?
Yes.
All right. We kind of lost it, but there's oxygen, oxygen, carbon in the center. Remember seeing that? So it's linear. Is it polar?
Yes. That's why they're different shades of color.
Is it polar? If you're going to, if it was on the exam, here it is.
It is polar.
Right?
What a workout.
All right. Is carbon dioxide a polar molecule? No, it's linear, right? So if you didn't have, I don't know, if I could get rid of just half of this, then you'd say it's polar. But no, this one cancels it out. Those tugs cancel out. So it's nonpolar. So if it's nonpolar, how can it stick to anything, right? Because only plus minus, you have to have some kind of dipole for it to stick. So this is going to be really weak interactions. So they're going to try to explain how dry ice turns into a solid. Something has to make it stick, right? Otherwise it wouldn't be a solid. So see how good a job they do here. Where'd it go?
Carbon dioxide, dry ice. Nonpolar molecules are arranged close to one another in a regular array where they move slightly around an average position. The distribution of electrons in a molecule can occasionally become asymmetrical, leading to the formation of a temporary
the pictures are all
separation
messed
of
up, though.
charges, a dipole.
Let's start it over. All the pictures are messed up. Where'd it go? Here it is.
In solid carbon dioxide, dry ice, nonpolar molecules are arranged close to one another in a regular array where they move slightly around an average position. The distribution of electrons in a molecule can occasionally become asymmetrical, leading to the formation of a temporary separation of charges.
So some molecule, one of these CO2 molecules in dry ice, for some reason the electrons just spend more time on one side than the other. And it's a very brief moment in time. It's like a billionth of a second is all this lasts for. But all that billionth, they said all disappeared. All that billionth of a second is all that it needs, is for that little dipole to be created. Then all of a sudden they all have these little dinky dipoles. So they're instantaneous.
A dipole. Partial changes on the molecule that form a temporary dipole then influence the electron clouds of nearby molecules. Although the dipoles are temporary, there is a significant attractive force between adjacent molecules as a result of the deformation of their electron clouds. These attractive forces are called London dispersion forces. London dispersion forces are the only type of intermolecular force found in nonpolar molecules.
There they are. So these nonpolar molecules, they have to have some type of intermolecular force. Otherwise they can't form a liquid, they can't form a solid. So their type is this London dispersion. Next is dipole-dipole.
Bonds between atoms with different electronegativities have a permanent dipole, that is, a separation of charges, because of the unequal sharing of electrons. Some molecules which contain polar bonds do not have a net dipole. For example, carbon tetrachloride has polar carbon-chloride bonds, but the polarities cancel as...
Remember that?
Yeah.
You'd call this polar or nonpolar?
No, nonpolar, because they
Call it nonpolar because they all canceled out. Or you could say no dipole moment was the terminology. You could say no dipole moment or nonpolar. But yet this exists as a liquid if you make it cold enough. So again, it's that London dispersion forces. It's not dipole-dipole yet. I don't know why they're giving an example of something that doesn't They
as a
are.
result of its symmetrical structure. It is therefore a nonpolar molecule. Even though the chloroform molecule has a tetrahedral shape, one of the outer atoms is different from the others, so the molecule is not symmetrical. This means the bond dipoles do not cancel, and the molecule has an overall dipole moment. It is polar. Molecules such as sulfur dioxide have asymmetrical structures due to one or more unshared pairs of electrons on the central atom. Sulfur dioxide is an asymmetrical molecule with polar bonds, therefore it is a polar molecule. When polar molecules such as sulfur dioxide are close to one another, they tend to align so that the positive end of one molecule points towards the negative end of another molecule. Attractions among polar molecules are called dipole-dipole forces. Bonds between
So they have to have a permanent dipole moment, then you call it dipole-dipole forces. That dipole is always there. It's not just instantaneous and happens for a femtosecond. No, it's always there. So it's a little bit stronger then.
So the driest would have been the London dispersion?
Yes, dry ice has to be London dispersion. The only reason is because it's nonpolar.
Oh, okay.
Yeah, and so it's momentary dipoles, and they'll suddenly happen, and they disappear. So, but it does not have a permanent dipole moment. So you have to say that's London. And they also call that London dispersion or van der Waals. I don't know why they have so many names for that extremely weak one for nonpolar molecules. Maybe because it's so complicated, it took a lot of people to figure it out. Okay, one more.
Okay, now it's just getting annoying. Sorry.
What's getting annoying?
All these videos.
Well, videos are good. It's all this hydrogen bonding. Last one.
Some polar molecules have unusually strong intermolecular attractions called hydrogen bonding. These attractions occur in molecules where hydrogen is bonded to fluorine, oxygen, or nitrogen. The interaction occurs between the hydrogen of one molecule and an unshared electron pair on the more electronegative element in another molecule. The orientation of hydrogen fluoride and water molecules in the liquid states of these substances is determined by hydrogen bonding. The hydrogen atom in hydrogen fluoride is attracted to the fluorine atom on another hydrogen fluoride molecule. Water, with 2 hydrogen atoms and 2 unshared pairs of electrons, can form 4 hydrogen bonds per molecule. In ice, hydrogen bonding leads to a tetrahedral arrangement of water molecules around one another, forming 6 membered rings that leave open channels through the ice structure. In liquid water, the tetrahedral arrangement is not fixed because the molecules are able to move around, and on average, a water molecule is surrounded by 3.4 other water molecules. Hydrogen bonding forces are unusually strong attractions that occur among molecules in which hydrogen is bonded to a highly electronegative atom.
And those electronegative atoms had to be, there's 3 of them. Did you catch it? Fluorine. Not chlorine. Yeah, hydrogen has to be there. Hydrogen and fluorine. Oxygen, there's one more. They're all in the same period. What's more electronegative than carbon? Nitrogen. Fon, F-O-N. Okay, so we can answer some questions now. So the strongest intermolecular force is hydrogen bonding. Okay? You have a molecule. How can you have something exhibit even more hydrogen bonding? Right? Well, let's back this up. What did you have to have in this molecule to have hydrogen bonding in the first place? H for sure. And what was it? What other elements? F-O-N, Fon. One of those. And then you're good. Then you say hydrogen bonding. Okay. How can I increase the strength of hydrogen bonding? So I have 2 molecules that are exhibiting hydrogen bonding. One has more hydrogen bonding than the other. How can that be? Hydrogen bonding is hydrogen bonding. Can you think of it? That's not an easy question. More, ooh, there you're getting there. More. Yeah, you could. That's a good one. More electronegative would be the F one, or more. She said more hydrogens. Someone said more hydrogens. More. For example, let's say, does anybody know what the active ingredient is in, I don't know, Coors Light? I just had one. Otherwise, the only thing I could. Miller. The cheap stuff. That's the active ingredient, right? What is it called? Yeah, but more specifically, there's an E. Ethanol. Okay. Does this molecule exhibit hydrogen bonding? Yes, it does, right? Because what do you see?
The hydrogens.
O and H. Okay, so it has to have hydrogen bonding. I'm going to change this molecule a little bit. Does this molecule exhibit hydrogen bonding? Does it exhibit, yes, does it exhibit more hydrogen bonding? Yeah, because now we've got two OHs. There's two spots for it to do its intermolecular force attraction thing. So that's one way to have more hydrogen bonding. Just have more OH groups, for example. But I liked crystals, too, saying how instead of having O here, have, what'd you say, like F or N or something, right? Something that's more electronegative than, you know. Okay, hydrogen bonding. What's the next strongest one? Dipole. How do you know, or how do you specify when, oh, this molecule is dipole? When there's a permanent dipole moment. Okay, now how do you know when there's a permanent dipole moment? Gabby, how do you know when there's a permanent dipole moment? This goes back to, I would say, that final exam that we took. And you had to look at that molecule, and you had to see if all the little dipoles canceled out. The symmetric, seeing if things are symmetric. If they are, good. Then you know it's nonpolar. Then that would be dipole. Has to be polar or has to have a dipole moment. That means the same thing, right? For example, I think they did. Oh, I can't have to draw it three-dimensional. I've got my carbon. Tetrahedral shape. Perfectly symmetric. So that means it's nonpolar. This would this exhibit dipole? It's nonpolar, right? So it can't. It can't exhibit dipole. All right. But what can I do to make it polar?
Add a lone pair.
Oh yeah, I could add a lone pair to screw up all the symmetry. I could just replace one of the chlorines with anything, just not chlorine again. And all of a sudden it's polar because things aren't going to cancel out. So dipole, it has to have a permanent dipole moment. How could you increase the strength?
Messing up the symmetry.
Yeah, you could make the symmetry worse or just make it more polar. How can you make a bond more polar? The E word. Electronegativity. Make the electronegativity difference even bigger, right? Like HN versus HF. Which one is a more polar bond? Which one, Tegan, which one is a more polar bond? HF, because F is the most electronegative out there. Exactly. So this is more polar than that one. The last intermolecular force is London dispersion, or you can call them van der Waals. But this is good. Okay. How can you increase this London dispersion force, the weakest one of the bunch? It's a hard question. I only think of dust bunnies when I think of this, but let's say you have two nonpolar molecules what makes them stick together? It's just stuff sticks to stuff,
Maybe
right?
change in
So if you could make the area bigger, it'll stick better. It's pretty much all you can do. Now, we don't know areas of molecules, but it's pretty easy for us to calculate the what weight? Molar mass, or the molecular weight. So we can calculate that. So we'll just go by that. If something's nonpolar, two things are nonpolar. The one with the bigger molecular weight will have stronger dispersion forces, because it has to be bigger. So it'll stick together better. I mean, it's going to be weak, but bigger molecular weight. Okay? Yes?
Since it's with non-polar molecules, could you just make it symmetrical? Would that also work?
Well, it has to be symmetric. It has to be symmetric. So then it makes, so this, you can't even talk about London dispersion being the only force unless it's symmetric, and it has to be nonpolar. And then you take those two symmetric things, and the one that has the higher molar mass, it'll have even more London dispersion forces. Okay. If which type of these forces would give you the highest boiling point, Tegan? Which one of these forces would give you the highest boiling point? Yeah, which type of intermolecular force would result in the highest boiling point? H bonding, because they're really tight, right? It's going to be tough, a lot of energy to kick them out into that gaseous phase. Which type of intermolecular force would give you, Alyssa, the highest surface tension? H bonding again, yeah, because you want really stiff bonds, right? So it's not going to stretch very well. No, that's kind of what we're thinking about. Yes, Teresa?
The non-Newtonian fluid,
Mm-hmm.
what was it, like zero left? I mean zero, the O?
Non-Newtonian fluid is just something that behaves exactly opposite of a regular fluid.
Okay.
So
I was just wondering why it was there.
it's really,
It was like very brief.
yeah, we were brief. Maybe because we forgot to talk about viscosity.
Okay. So.
We skipped it entirely. Okay. Yeah. Newtonian fluid has exact opposite behavior as other liquids. When we think of what do you think of when you think of viscosity? What's that? Stickiness. Something that's really viscous is really sticky. It doesn't move, right? It's really thick. Okay. If you're in viscosity is the word that they use all the time about oil. You're changing the oil in your car. Minnesota right now, you better put a very viscous, a very highly viscous, or a oil with a very low viscosity. Which one would you put in right now? It's extremely cold. High viscosity?
Less.
Low viscosity.
Yeah, in order for it to move.
Because you got to lubricate all that entire engine, and it's extremely cold. That stuff is already very viscous. So you want to get the lowest viscosity oil you can find, and that's what you put in your engine right now. Okay. Texas, we don't care. It never gets that cold. At least it didn't until last week. Okay. I think we covered most everything there. Identify each intermolecular force acting below. So all this they're trying to say is you have HCl, you have this compound. What intermolecular force would be acting in HCl? Erica, what would you say? What type of intermolecular force acts with HCl compound? Wait, excuse me. You have the hydrogen, but you're missing one of the other three. So it would have to be the second one. Because this has a permanent dipole moment. So it would be dipole-dipole. How about H2O? Gabby, how about H2O? Hydrogen bonding, good. How about C? C is a gecko hanging on a piece of glass.
That's that.
Danny, which one would you guess there? That's why I put the picture there. But then it's wrong.
What?
Because the picture was from, and then these guys doing research on it. So you had to actually get into it and read it some more. Everyone always thought it's dispersion. Everybody did, right? But it's not. They had to cut off those poor little toes on that thing. And they analyzed them all, a whole bunch of these geckos. And it's not dispersion, it's hydrogen bonding. And it kind of makes sense because you're holding a big, heavy gecko on a hunk of glass. I mean, it's got to be pretty strong. It can't be dispersion. So it's hydrogen bonding. That's kind of a trick question. Okay. Heat of vaporization of certain liquids are 20.4, 0.9, 5.6. Are they in the order you would expect, where this one's the lowest and this one's the highest? Is it what you would expect, Sabina, knowing what you know about intermolecular forces? Okay, now the trick to answering these types of questions in the homework is to look at each compound and identify what type of intermolecular force it has. So chlorine, hydrogen, and nitrogen, they all have the exact same intermolecular force. Which kind is it? Has to be London dispersion. Because all of these are what? Nonpolar. They're all nonpolar. So it has to be dispersion. So you're supposed to go by what then? What do we say? The weight. The one with the biggest weight had better have the biggest enthalpy of vaporization. And it does. Chlorine. The smallest, hydrogen. It works. Here's another example.
Wait.
Yeah.
What did you say? The biggest weight something. Yeah, the biggest weight what?
The biggest molecular weight will have the biggest dispersion. So if it has the biggest dispersion, its intermolecular forces is the strongest. So it's going to be the toughest to, in this case, boil. Turn from a liquid to a gas. Enthalpy of vaporization is just to go from a liquid to a gas. That energy that's needed. So take a look at this next one and see if you can figure out why this one makes sense. Same thing, enthalpy of vaporization, heat of vaporization. Going from a liquid to a gas. For O2, it's 6.8 kilojoules per mole. Neon, it's 1.8, while methanol is 34.5.
So these are also London dispersion.
I don't know, you have to look at it and see. Take a look at each molecule individually and see what type of force it would have. What's that?
Is it one of each?
It could be. O2 is definitely nonpolar, so this would be what type? London, or dispersion. This one's definitely London. So I'm not even looking at the numbers yet. Just identify. Neon would be, it's just neon though.
Oh, so there's nothing.
Yeah. You need, for it to be polar, you need to have two atoms, at least, at the minimum, two atoms that are different. And then it's polar. If you have a whole bunch of atoms, then you got to look at the dipoles and see if they're canceling on you and look at symmetry.
So what are we explaining?
So which one is this one?
Nothing.
What type of intermolecular force? It's nonpolar. Has to be London. It's nonpolar. Then you have methanol. H bonding. Oh, so not even, don't even look at the numbers. You expect this guy to be the highest enthalpy of vaporization. These two, well, so whichever one has a bigger molar mass, he'll be bigger. And oxygen is bigger. He's 32. Neon is only about 20-something, right? Grams per mole. Okay. That's what we did. Yeah. Why? Why is methanol the biggest? The answer is, you would write in your homework, hydrogen bonding. Yep.
So, Fermionic by itself, any molecule by itself is going to be
London. It's going to be nonpolar. Exactly. Every single time. Alrighty, so come to get some free pizza. It's right now.